So we saw generators, mostly periodic generators. We saw additive synthesis, and we also introduced filters like a specific family, just as an example of a specific family of fusions capable of transforming input audio streams. Now, I think an interesting elements that we have not discussed yet concern the how to read sound from out of SuperCollider. Now, an issue that can be and must be addressed by taking into account buses. So we have to go back to buses. I was looking for an image, and like this image, where is it? Server. This one, I guess. Yes, the one we already discussed in previous videos. And what happens here is that we have a picture of the objects that are available on the server and that we are controlling. So now we know that we are controlling synths that here are not represented, but that can be represented as a project to be stored into an archive. Like here inside our server there is an archive filled with synth, and here we have synth as connection of UGENs, and for the moment we are sending out audio signals to the out buses, and we saw that we can use 0 and 1 as our bus indexes, meaning in a classic typical stereo setup we have left and right, and we know that we can keep on using these numbers to represent buses. So we have if we have an 8-channel sound card, 0 up to 7 are the outputs of our sound card. Now the question is, how do we get sound from outside our computer? Typical situation, through a microphone. The point is that, as you can see in this figure, there are also in buses, meaning they are pipes like out buses and like internal buses that we will not introduce here. That's not in particularly complex, but well, we have no time for the moment. But the question is, how do we get to these buses? We know how to address these out buses because we can use numbers starting from 0, representing EDs of the buses. But which are the IDs of the in buses? Well, actually the situation is as follows. So you have 0, 1 that represents outputs of your sound cards. Once you have finished the output of your sound card, the next ones in our classic stereo setup, meaning 2 and probably 3, represent the input, and all the numbers greater than the last bus index are dedicated to internal private buses. So what should probably happen on your sound card is that this is the left channel and this is the right channel, meaning out bus first, and out bus is first and second. Then you have no other outputs from your internal sound card, the internal sound card of your computer, and probably you have a microphone just like the one you're using for Skype, and even if or for Meet, whatever you're using for, and even if a microphone typically is mono, a microphone on a computer typically is stereo. It is just duplicating the input signal on two channels. Why? So you avoid having a conversation via chat, via Skype, just to say, in mono. This would mean that it will come out from a single loudspeaker. So typically it's a sort of false stereo, two channels to represent the same signal. And so suppose we want to read what is going on here. What can we do? Well, we should read this bus here. Now let's make an example. Let's go directly to practice. So we make a synth. Well, what happens actually is that rather than making a synth, we try to scope the server and see what happens with its buses. You know, this is a typical situation of scoping. Now, this is the starting bus, which is a 0, so it is the left channel, and this is the number of buses to be scoped. Now here you have 10 because the sound card I'm using uses 10 out buses. It has 10 physical, not buses, physical outs. So by default, what happens with stethoscope is that it displays the number of the outs of your sound cards. Now the point is that we want to see the ins, and the ins are after. So maybe rather than scoping 10 channels, we can scope more than 10 channels, like here. And here something strange happens, because as you can see, there is one signal going on here. So actually those pipes is just like they are buses connected to the out, and we are not writing anything here. But here it's just like we have pipes coming in, and in this case on the first input of my sound card, it's a mono input of course, I have a microphone in order to speak and to record, and here you see my voice generating that can be read as a stream. And of course I can have more input in my sound cards. I think I have something like 8 input. So if I have 8 outputs and 8 inputs, then internal buses are those going from the 17th going on. So how do we read these? Well, you might think that we have to read from the bus number. Well, in this case it should be number 8, starting from 0, the 8th bus. But this would be a setting that could create some issues, because suppose you're changing your sound card and using the normal stereo sound card, you want to read not from here, but rather you want to read from not from the number 8, but from the number 2 probably. So the point is that your code for reading the first input should change if you are changing your sound card. This would be a little boring. So actually by convention we have a Eugen like this, which is sound in, which is capable of reading the input of your sound card, and the number you're passing here, you see it is bus, it is not 0. 0 here means the first input bus. Thus this code will read the first input bus with no respect to the sound card you're using at the moment, because it will read always the first input bus. So this is a 0, meaning the first input bus. It's not meaning the real index of the bus. On the bus there's a component called bus allocator that says that assigns numbers to the buses, and in my case this would be the bus number 8, that is the number 8th, that is the 9th, because I have 8 outs, and this is the 9th bus. So this is pretty easy to use. And now what we are doing is that by means of this Eugen, we're going to take the first input available. We're going to read the first input bus. On this input bus, I'm sending via hardware, via the sound card, the sound collected by my microphone. So now we will have some feedback probably. Yeah, in fact we have to take into account this, but it's interesting for us. And what happens is that you can see that this is the input bus, and I'm writing this signal by means of sounding here in output bus 0. So from here I am in some sense routing this here. Why? Well, actually, let's stop this, because you know that this function play means that we are creating a temporary def which is adding for us something like this. Now this would mean that on the output, on the bus 0, that is the first output, we are forwarding this signal. This signal reads from the first available input, which is, that is why it is 0, but it will not be 0 in terms of the overall number of buses, and it is routing this bus on 0. So that's the way we can read from inputs. And of course you have various input, you have various microphone, you simply read on the various inputs of your sound card in this way. So the thing to be kept in mind is that the first buses are out buses related to your sound card, then the input buses related to your sound cards follow, and then all the other available indexes are for private buses. So that's the way we can this is a way in which we can create an audio stream in real time from the input of our sound card. Now, what to do with this? Well, we can do various things. As an example, I can do something like filtering this, or maybe like with a band pass filter, and this is my input source, because it is a signal created by sound in. So with frequency, let's say 100 frequency, and well, we could control this mouse YKR 70 500, and here a very okay. So we are filtering and controlling the central frequency of this filter by means of the mouse, and the source here is my microphone. So I don't know if you can listen, no, because we are losing a lot of energy. So we can add something here, like let's say 12 dB amp. Okay, so maybe we hear something more. No. Well, yes, you can see it. Actually, it's more difficult to hear. The point is that this is quite strict. Let's do it. Okay, so now it's easier, and you see it's still very the bandwidth is very a small one, and you see we're using it's a noise used, my voice used as a source. Now we're having some feedback. That's the point, because the sound coming from a loudspeaker are entering into the microphone, a typical issue you probably know. Right, once we have this, we can surely do many interesting things. And so this is a possible way to use other kind of sources in your project if you are taking sound in real time from external sources. Now, concerning sources, because we started our discussion speaking about sources for filters, and so we say, okay, which are the sources that I can use? Surely sources are sound I generate internally from generators, be those generators periodic like pulse or sinus, whatever, or be there noises like white noise, brown noise, and there are many other noise generators. Another possibility is to use input sounds. So once beware that once we have something like this, what is going out from here is a stream of values that can be treated like a sinusoid, whatever. So once we are inside the server, it's the only thing that we have to think about is that we have stream of values, in this case at audio rate. And of course there is a third source that can enrich a lot the palette we can use to create and manipulate and organize sounds, and are sounds that are already recorded and available on your computer because you recorded them, because you have extracted them from by means of other softwares like audio editor, or that maybe you have downloaded them from various sources. A very useful resource for sample is freesound.org that I always suggest, because it's a community uploading samples, so you can download. You got description and you can download for free these samples. So suppose we have a sample. How do we load this sample in SuperCollider? And here it is necessary finally to speak about buffer. So take a look here at this synth. We have it's a synth, so it comes from a project. This project should have described this structure of Fusion by means of the Fusion graph function, by means of patching, as we know. But as you can see here, there are two objects bearing the same name, which is buffer. One is internal and the other is external. Two ways in which this can work, but the substance is always the same, because the topic here is that we are using a buffer. What is a buffer? It's a temporary location of memory allocated by the server in which we can store data. Many things can be done by means of buffers, so you can store various kinds of data. You can also generate data and store them into the buffer. But the point of the buffer is that it is a memory location, meaning it's just like a store, like a deposit. You just place things there, they stay there, and if you're in need to, you can use these data. So what is the typical usage? Well, the typical usage is to fill a buffer, meaning to reserve an amount of RAM, a location, for loading a file from an hard disk. So suppose we have a file, an audio file, and I can try to find an audio file here. So suppose we go on our specific where is it? Recordings. Here we can have well, this is a drum machine that I sampled, not in a very clean way, but anyway, this is the path of that I have on my machine of a sound file. Maybe you want to know which sound file this is. It's a kick. It's a synthetic kick. Now I have dragged the file into the editor, and this behavior resulted in having available as a string the path of the file. So you want to load a file in SuperCollider, first things you can do is simply to drag the file over the editor, you get the path. The path is not enough, but it's a requirement. Then you need to create a buffer. Buffers are objects on the server, but of course, as usual, we have a linguistic representation of this object. Thus, we have a buffer class that can do many things, and this you can understand that this is a method for the class, so it's a constructor method. It returns to you an instance of a buffer that is a single buffer you can work with, you can address. We should assign these to a variable. We will use the classic b for buffer, and the parameter you have to, the arguments we have to pass are at least two. The first is the server itself, because the buffer must be loaded onto a server. Now you say, okay, but there is only one server. That's not true. You can have many servers, many instances of the server you can control. Well, it is an advanced usage, but the point is that you have, as you can have more instances of the server, you have to specify on which server you want to load this buffer. So we have one, the one assigned to S. So here we pass the server and here the path. Now B is a buffer. What can you do with a buffer? You can check this simply by doing this, and it should sound. Now, the typical things I'm doing is that I'm normalizing. So here I will override the buffer. I am normalizing the buffer, so I'm sure that they are at maximum amplitude. That should not change a lot. Yeah, a little bit. Now, bplay, buffer play. Hey, buffer play yourself. What does this mean? We know that in order to generate sound on the server, we need a sendef and a send. That's what this is doing for us, exactly like function play. Behind the scenes, there's the creation of a temporary synth that is able to play back a buffer, and this synth is created for us. But of course, it is important to understand how to do this properly and directly, because there are many things that can be manipulated by using buffers. So there are various agents capable of reading, and by the way also for writing buffers. We're not interested in our case in writing. The most basic and still very, very useful is this one, which has a very meaningful name, playbuff. It's a playback agent for buffers. So playbuff R. And as you can see here, there are some arguments. The first is the number of the channels of the buffer, so you have to keep track of this. I know that my samples are mono, so I will write 1. Then you have to pass buff_num, buffer number. Actually, it's just the buffer, the variable associated to the buffer, so we can do this. And then there are other parameters, but first of all, we have to create something a little bit more articulated. So we made a player. We call this synth player, and what is happening now is that we have an argument which is out by default 0. Then we will have buffer, and that should be passed from outside. Let's start with this. And of course, what we have to do is to send out our signal. So the point is that this agent is generating a stream of values by means of reading the content of the buffer. So let's see here. We have a player like X synth player, and we have kick. Again, kick. Fine. So what happened here is that by evaluating this many times, we have 4 synths. So our synth is still active. Now, interestingly enough, play buff can be, it's huge and it can be typologically related to now our notion of event. Well, not necessary, because you can have a player that is resident and you just providing him various buffers. So you have one synth and then you change the buffers and you stop it and you start playing again and so on. But another typical possibility for a Eugen like this is substantially to act as a sort of envelope for a playing back of that samples, and this envelope is related to the samples, meaning once the sample is finished, we do not want to take into account the synth, so we just want to do something like this, playback and go away. So not surprising, there is an argument which is, guess what, done action, and so we can have a player like this that simply envelopes the playing back of the synth. Now in this case it's useless to assign to a variable. Fine. So there are other very interesting argument here. So as you can see, there is at least there is rate that we have to take into account. Rate is the speed at which you read the buffer, where 1 is the normal speed, and if you have 2, it means that you're reading at twice the speed, just like with a tape or with on a turntable if you're varying the speed. And of course, if you're reading faster, the buffer, the generated sound will be shorter and with a higher pitch. And if you're reading slower, you will have lower frequencies and longer duration, so the 2 parameters are coupled. And well, we can understand something about these frequency ratios, because if we're doubling the speed, we have half the duration, then we have an octave higher, while if we are doing something like this, we have 1 octave lower, because we are reading at half the speed. That's interesting. So we can have rate here, and this rate can be passed in here, and we have a default value of 1. So let's see if this works. Okay, so what can we do? Well, we can have a snare like this, and we call this C, and C it's buffer read S, and let's see if we have something interesting. We can have like this is a rim shot. Let's use also this rim shot. So D is buffer. So we have three buffer. Let's normalize everything. So now, okay, so what can we do? Well, actually, of course, all the algorithmic capabilities that we can use are available here. So let's do simple routing to understand what is going on, and our simple routing will do something like inf.do, and no, Control Z, and here we want to do this. Should not be, it should be this one. Okay, let's wait for something rather than 0.2 2.weight, and here we can decide to pass as a buffer something like B, C, D, choose, random choice, and random choice of our buffers, and that's fine. Infinite times, just play this back. Now this is a bit boring because it would be more interesting to do something like 0.1, 0.2, maybe 0.3, choose. Let's see. Okay, there's something that does not work here. Yes, it says we were passing B, right here we have to pass buffer, which is the variable argument from external. Of course, we can have more complex structure. Again, maybe it is better if we make this a little bit more complicated, in the sense that we want to have this stereo. So this is our in. We are adding keywords so it's easier, and which is and maybe here we have position, that should be pause, and maybe here we can control directly level, that should be amp, and we say that amp that pause equals 0, so standard stereo level, and amp is 1, but we can control this. If we this is a classic pan 2, we're missing right, we're missing a parenthesis. Okay, maybe let's do this in this way, it's easier to be read. So now what happens here is that, of course, pause can be -1 around 1, while well, level can be something like -6, the -6, no, this should not be rand, but rand, between rand 0 dB amp. As target not understood, because it's not called level, it's called amp in the end of the argument. No. Too fast clicking. So pause amp, is it pause? Yes. So what's going on here? Symbol pause, buffer pause, send of player, that should run. No. Okay, let's try to debug this. So we get as target not understood, symbol pause. So synth player. Right, this is wrong. It's typical when we add a bit randomly and interactively arguments. There was brackets which was closed before. Well, you can also define units. Like we can say that we have single units and we want to choose between 1, 2, 3 and 4. Let's consider this as 16 in music. This is 1/16, this is an 8, this is 3/16, and this is a quarter. Fine. Now the point is that we want to use this in relation, and choose randomly between these, maybe in relation to what? to let's consider a tempo expressed in BPM. BPM means that our unit is to wait. When we say that we are at 60 BPM, it means that 60 BPM. It means that our unit is 1 second. So there are 60 every minute. So each bit is something like 60 divided by 60. What happens if we increase the tempo? Let's suppose we are at 120. It means that in 1 minute we have 120 bits. So each bit is how much? Is half a second, not 60 divided by 60, but it's 60 divided by 120. So the point is that we can have a BPM, and we can decide that this, not PBM, but BPM, let's start with 60, and then we can say that here we multiply these, we use these, we say that we have a variable which is unit, and every time we see that unit is checked, and it is BPM divided by 4, because it represents 1/16 here, so we want to multiply this so that 4 here represent 1 BPM and 1/16, so per unit. This should mean, in our idea, that we are able to control the BPM externally. No? So what happened? BPM has not been assigned. That's the point. What's the point here? A bit too much. BPM. No, we there's been the typo somewhere. This should be BPM. Should be BPM 60 divided by BPM, so we get the duration of 1 unit divided by 4. So suppose we're gonna want to go at 120, doubling the tempo. I'm not sure. Well, let's do this. To be sure. Maybe yes, but let's check this. Let's exaggerate. Yes, it's faster. Maybe we can have interesting like 1 1 3 1 3 1 4 1. This could be our rhythm. Rather than randomly selecting, what we do is that here we use this one rhythm, and we are accessing these by means of E modulo size per unit. We are not choosing anymore because we simply want to wait the right time. So we have a rhythm. Then the point is that I'm missing my rhythm, and it is here. So let's stop this. So we have a rhythmic pattern defined in terms of 16. 1 1 2 3 2 4 1. Well, actually this would be this works. Okay, so here we are accessing as usual by means of the counter, which has still to be specified. Here it is, and we're wrapping around this rhythm multiplying these units, which are basic units, like we were using 0 to represent our root, and then we were transposing it. Here we're using it by multiplying it for unit, and we wait. Let's see if this works. Okay, but why don't we can still do something very like I modulo 3? Well, that's, and let's see if we have some more specific rhythm. Now, in this way, we have always the same elements, but they will be read in this sequence, which is a sort of asymmetrical one. Now that we can change this. This is 216 and 18. Pa-pa-pam, pa-pa-pam, pa-pa-pam. We can change this in real time, you can see. Now we go with 32. If you want, you can have something like an acciaccatura. And so on. So that's an interesting aspect of using samples. And of course, here I'm doing a sort of drum machine, algorithmic drum machine. But of course, you can load whatever you want. I will still keep on using. Percussion samples, but in this case what I'm trying to do is to use a classic of mine, which is probably this one. Okay, this is good. Let's see bells. Okay, so well, suppose we have something like well, here the point is that we're going on assigning to variables that are more structural approaches by means of using arrays. I'm not discussing this. I'm leaving this to you. Let's use this one. Well, this is ink, and let's use Shoko. Nice one. Where am I with my mouse? I'm losing my mouse. So Shoko, it's here, and this will be Shoko. Buffer. Read S and normalize. So yes, another one. So what can we do with this? Well, of course, all the things we saw, our player is still at work. We're using this event-based pattern. You have probably, I guess you have understood that I like this idea of generating things rather than controlling instrument. This is a kind of preference I have, because I'm more related to composition than to tweaking on knobs, so that's kind of the different attitude. So let's do something like synth player, and the arcs are that buffer is ink. Now, okay, cool. And then it's a very long one. Let's consider rate now. We know the other argument. Rate is interesting. Rate. Normally default is 1. So let's do this in this way. 1 octave. 1 octave below. Oh. This is very interesting. The point is that when we are dealing with octaves, everything is so clear by divide or multiply by 2. But what about doing half step? Well, you have to do some calculation, but luckily there is something very easy. So let's do this. Let's assume we have a conversion like this. We start from 12 and we have a MIDI to ratio. This means that we are interpreting this as MIDI, and we want to go to ratio between typically frequencies. In our case, reading frequencies. Let's see. You will see a strange number, but actually it's just the standard approximation for 2. And this is good. This means that if we want a ratio representing 12 semitones upper, it means that the ratio that has to be used to read our sample must be 2. So what happens is, if we want to go down, so minus 12 semitones, 1 octave below, actually we got, well, this is the approximation. We don't care about these small numbers. The point is that it is 0.5. Well, this was easy, but actually what happens with a major third? You see, it's very nice to be able to work in this way, because, by the way, we can do things like this. So let's see, we have 1 rate, then we have MIDI. This is we are reading like it is transposed of a major third, and here we do a major chord of samples. Let's see if it works. So of course, point is we want to play all these 3 scenes together, 3 events. Well, that's interesting, a bit too high for us. So let's do this like having 0 MIDI ratio, because 0 MIDI ratio means transposed to nothing, so same pitch, so it's 1. So that's fine. Let's do this in this way, and in this way we are transposing down 1 octave. Cool. We want, if you want the minor version, minor third, and so we can have very interesting things going on here. We can do the same thing, by the way, with Shoko. Of course, we do not know which is the absolute pitch. We should estimate this, because we do not know. But the point is that Shoko is less It's less interesting. Yeah, because okay. So point is that this shows you that the quality of the material is very important, because inking is very pitched, so we get very easy. We have harmonies, while Shoko is more complex, but like, so it's more complicated to have. It's like this. This is one. So well, we can have something like let's suppose we have a male. Let's use our classic approach. Then we can do something like array. No, let's call this voice. We did already something like this, like array fill 4 with what? With routines, which are infinite times do what? They should have a counter like arg-e, and we do mel and access. I will show you some mistake here. I modulo mel size, so we keep on doing this. This should be used to do what? To take our saint here, and we will use this as then we have to wait something, and in our idea, what the hell is this? In our idea we have to wait for something like well, this approach was interesting. So it was unit, and then what happened is that, well, we can have rhythm like this. Why not? We like this, so we place this here. Fine. Then what was this one? The block was this one. Okay, so we're still using. The point is that now they are playing the same, while midi ratio. Here we should use something like this counter. Mel size minus CNT times 12. And unit, we will multiply unit for CNT plus 1. I don't know, actually. We should have made a bunch of mistakes, but you see we are prototyping code. Unit not defined, that's true. Var unit can be defined at which level? Here. Let's see. Syntactically it's fine. Voices. So we're mixing some of the approaches we have previously seen. Voices do. Oh no, not exactly. Arg v play. We reset play, so we're sure we start back. We get routing, and let's prepare. Let's be prepared for a stop. All right. That is easy to. Okay. Voices. Voices inside my head. This is police. Let's go slower. Now here we're using voices, and well, the point is that unit is interesting because it depends on BPM, which is defined outside this. So maybe we can use this also for well, let's do this in a very clean way. Okay, then of course we can have various routines, like we can have something doing infinite time do fork, and we have because we have also Shoko is interesting, so we can have let's take this and we create a layer like this, and let's make a small composition. We will not change this in unit per unit must be this one. So let's do this. We want to have very slow bells, so we're, and this should be greater than divided by 4, should be by 2 multiplied by 2, so it's very oops, yeah, but it could be slower. Let's do this really. Okay, 2 octave lower. Again. So, oh yes, we like this. We're not using the stereo. We can use this stereo placement because here the point is that we're using this. Let's try to be a little bit. It will not be so easy. We can use pause and use pause to position to differentiate our voices. So could be something like C and T that should be mapped from 0 to 3. You see that lean, it's pretty easy to use, between -1 and +1. Okay. Let's do this with 6 voices. Fine, this is sort of gamelan style thing, but of course we can add something, and we will just, as a way to understand what is going on, we will have our player, and every of these beats we will wait for, we will take this from was B, C, D, D, B, D, C, B, E, modulo 3, 6. 6 arc y. Rate. Well, it's interesting to see what happens if we have something like this. Yeah, because we are working with pitches, but now here we are working again with BCD that represent percussion. So let's try to see what's going on here. It's very low. Not particularly interesting. It works very fine with... Yeah, it's quite filled with artifacts, so not very interesting to work with rate here. So we will not use rate, and we simply add a layer. Now three. Here we're missing something. This is fine. This is fine. This is not fine. Let's give a little bit divided by 4. That will be a bit intensive. And here we could have something like we have buffer, but the position could be interesting, like we have uno dot neg okay. You can go. If you like it, you can listen to this for infinite time. You just stay there like a Buddha and hearing to this sort of gamelan things. The last thing I want to show you is always in this idea of working with samples and how to mix up these two things. Well, it's pretty easy at the end. But well, suppose you are here and you are taking some sound from your microphone. So in this moment, if I evaluate this, sound in goes to the bus and creates a stream for me that can be used. What about recording? What about recording from SuperCollider output? Well, there are many ways you can do this. The easy way for fast prototyping, etc., is going here and start recording and end recording. So let's see what is going on. So, okay. So, we have recorded a file. Where is it? Well, if you go here, you see that there is open user support directory, and there is it opens a directory of installation directory, and here you have recording, and this should be mine. Well, so now we have a file and we can use it, and we have a player, and let's look back to our player so we can add some variation to it. So rather than using action 0, this time we will use this loop. in play buff means that it keeps on looping. So when it reaches the end, it starts back, wrapping around. So of course, saying loop 1 meaning that it is looping, and writing done action 2 is a contradiction. You can do it, but it's conceptually wrong. So the idea is that or you're deleting everything or you're looping substantially. So we have that's why we have eliminated done action, or technically done action is 0, so keeps on working. So now we have a different player, and what happened is that we can have a sample void which is buffer read. Where is it? Here. First we have to prepend the server. Do we need to normalize this? Let's normalize this. Now we can have something like synth player and buffer vo. Okay, so can we experiment a little bit with this idea? Well, sure. Let's create just one synth. Play buff R. What can we do with this? When we can have an array fill, and let's say 4 arg a. Now what we are doing, I did something wrong here, is that we are using this to play back. This is not mono because it is recorded as stereo. This is something I know, because even if it's mono, it is recorded as stereo. So we can do this in this way, and it will be vo. The point is that we will use rate, and rate will be something related to our counter e multiplied by 0 2 and loop is 1. So let's see what's going on here. Yeah, there's a mistake here, of course, because we need to mix this. var sig, and of course mix sig. Then we can do something like pan2. No, this is wrong. pan2 source. Fine. This is interesting. What I do not like is the fact that probably it is because it is stereo, I guess. Because sig is an array, but while mixing we get still this mono. So there is red, I think there is red channel. Let's see. Yeah, and it's let's see red channel. Let's try to find this. Okay, we go to buffer, and we have red channel, server, path, fine, channels, an array of channels to be read. Index start from 0. This will be read. So you can read multi-channel file. We simply read one channel, and we add channels, and we want, it's an array, so it should be 0. Let's see. So now we need to play this in this way. Now it's stereo. Let's exaggerate a little bit. We get 12 cobble, 12 strange aliens or strange creatures. You want a band of 20. Let's start. Let's make them really low. So what happened here is that we're creating 20 players. Those players, they all read this VO buffer, which is something we did with my voice. We are reading this by multiplying I. Well, maybe it would be better to do something like this. Multiplying I should not start from 0 actually. I for 0.1, meaning that 0.1, 0.2, 0.3, this is really low, because you remember that 0.5 means half of the standard reading speed, and we're looping. So and we're doing this in one. We're doing this in a simple step. Can get complex things. So we know that. Well. Like you got a bottle, but let's use a beater. It's very high. Cool. Now, accidentally, I've added some noise. This will make our sample more complicated. Well, of course, you should edit your sample. I'm not editing the sample. And let's use this approach again. Now at this point we use a new, this one. You see you have recording data. It's pitched. It's a sort of process. This is not continuous in some sense. We've got a coming from the background. And so on. Well, I find this fascinating. Maybe it's me. But of course, this idea of using materials you can find, and by the way, of course, the quality of recording can be important, but sometimes it is not. Sometimes it's the idea you're making, because at the end, it's just the way you manipulate and the way you use this spectral organization that is important. So there's wide room to record the things you like and you have available in order to make sound. Let's make a last example, like here we are again with our microphone, and what we can do is start recording. So now we have a snap of fingers. Here it is. Of course, it's the same process. It sounds like dropping, water drops almost sometimes. So there are plenty of things you can do. Of course, all the things you can you know about sound processing and sound synthesis. They all can be used inside SuperCollider. Substantially every kind of sound processing techniques or sound generating method for sound synthesis can be implemented in SuperCollider. Many times it is already implemented into SuperCollider. You just have to find out typically a specific region. Sometimes you can look on the web and you will find help. And if you need help, remember there are a lot of resources online. There is a very responsive official SuperCollider users mailing list. There are also Facebook groups. There is the international one, there is the Italian one, maybe there are also, surely there is one in Spanish. There are also other probably related to other languages. You go to the site, you find all the resources, and remember to use the help files. The help files are very important. There are many help files, and you can dig into these help files and find a lot of information that can be directly used. So I guess I could say right now, well, you know where to contact me, and so have fun.